As we begin this section, the question we're trying to answer is, how does the position on the periodic table affect the nuclear charge that's seen by the outermost electron? So that is the concept of effective nuclear charge. It is symbolized by ZeFF, and it indicates how strongly electrons are attracted to that positive nucleus. So this force of attraction, which is Coulomb's law, it depends on the magnitude of the charges and the average distance between the electron and the nucleus. So we've learned a lot about the modern structure of the atom. Keep that in mind as we walk through here. In a many electron atom, know that each electron, it's simultaneously attracted to the nucleus and it's also repelled by other electrons. So you have these two forces that are going after each other. So what we're going to do is we're going to estimate what could be this effective nuclear charge of each electron. And there's a formula. It's sitting down there. Essentially, ZeFF is going to be equal to Z, which is the number of protons, minus S, the number of electrons, where S is going to represent the core. That is the noble gas that we wrote in the electron configuration. So these are the pictures from your textbook, and I'm going to say a couple things about them. Here we have the formula. Here we say Z is the number of protons from the periodic table, and again, S is the number of core electrons. If we were to look at the simplest model, we would see that as we walk across the periodic table, as the atomic number increases, so does the effective nuclear charge. Now again, we are Gen Chem. If we use a more sophisticated model, we are going to get a different type of understanding, and that would be these blue and these yellow lines, where when you finish a row, what happens is you start from scratch. I'll talk about that in a second. But this concept, students have struggled with it, and what they use in your book is they say, imagine there is a light bulb that is the nucleus, and imagine that you can control the amount of frosting on the bulb or glass surrounding the nucleus. What is your eye going to see? So I went to LibreText because I liked their explanation a lot better. So we will say, first of all, we have a positively charged nucleus. There is where it points to it. Then what we have is we have electrons in between, and they're going to cancel some of the nuclear charge. And then we have our electron of interest. We also have electrons on the outside, but they have absolutely no interest. That's our electron of interest. And that normally is the one taking part in the chemical reaction. It's the electron in the highest shell. So in terms of explaining this shielding effect, the core electron, it's going to repel that outer electron, and it's going to lower the effective nuclear charge of the nucleus on it, and the nucleus has less of a grip. Again, I got this from LibreText. You can Google it. It's a free resource. And once again, they show just what we have in our BLB. There is our increase with atomic number, how the effective nuclear charge increases, and then also as you go down to a row, how things happen. Well, I've learned that's sometimes just not good enough for some students, so we'll just have to sit with it for now. As I prepared this, I was going to walk through this entire argument, but instead I'm going to direct you to problem 714 in your book. Let you read about it, let you think about it. I think that's possibly most important. Finally, here's another question. It says, arrange the following atoms in order of increasing effective nuclear charge. When I look at it, I thought, gosh, what are we going to do? But again, I could tell you, but I do think it is more important for you to think about it and think your way through. Please ask questions. We're always open to them.